This video will cover dot product, angle between vectors, as well as the projection of one vector onto the other. So we're going to cover the next 3 pages in our notebook. And on the first one, we're just going to write down a couple of things, things that we need to know about vectors for the upcoming test. The first thing is formulas that we need to memorize. The big one that we need to memorize is the dot product. So for dot product, we're going to get our two vectors and we're going to multiply our two vectors and we're going to actually just get a number. So, and we'll talk more about what this means in a second, but we get the x components of each of our vectors and multiply them, and then we're going to add it to the product of our y components of each of those vectors. And the big thing to remember is that this is just a number. It's no longer going to be a vector. The other formula that you need to memorize is the angle between two vectors. And what we do is we're going to have cosine of theta is going to equal to the dot product of my two vectors divided by the magnitude of each of those vectors. So remember, we can denote magnitude with double absolute values or single ones. Either one will work. So these two guys we need to make sure we know and memorize. Another formula that we're going to talk about is a projection of a vector onto another vector. And for that one, I will be giving you that formula so that you don't have to memorize it. Big thing to know about this one is that if you have a vector, we can decompose the vector into two other vectors. We'll call it v1 and v2. Now, the big thing is that we want v1 and v2 to be perpendicular to each other, and they're going to make up my vector v. The other thing is that we want it projected onto another vector. So what that means to us is, let's say we have vector w here and we have vector v here. So what we want to do is we want to get one side of my projection, right? So we're going to put it right on top of here, and we're going to create this vector here, and this one is what we call vector 1. Notice that vector 1 is actually parallel to vector w. You can see that they're going in the same direction, the same slope, so they are parallel to each other. They're not equal to each other, but they are parallel to each other. We can also create this vertical component. I put that in quotes because it's not quite vertical, but it is perpendicular to the w vector as well as the v1 vector, and we'll call that one v2 vector. So that gets me my v1 and v2 are perpendicular to each other, and we have projected a component of vector v onto w, or vector w. So we know those two things. So what we can find out then is that vector 1, that can be found by getting the v vector and the w vector and doing a dot product with them, getting the magnitude of w and squaring it, and then multiply it times vector w. So this formula here will be given, but you're going to have to be able to use it. For the next 2 pages in our notebook, I suggest that you print out the handout labeled dot product applications, and we will work with them together. So what we're going to find out here is that if we have vector v and we let vector v equal to a comma b, and we let vector u equal to c comma d, then you can find the dot product between u and v vectors to be a c plus b d. So you're going to get the horizontal components and multiply those together, and then you're going to get the vertical components, multiply those together and add, and remember that equals to just a number. before we go on and do some more multiplying of vectors, let's talk a little bit about some of the properties of vectors. One big one is that if you are doing the dot product of u dot v, that it's the same as doing the dot product of v dot u. So the commutative property of vectors still applies. We also find that if we are going to add vectors and then multiplying them, we can also do the distributive property with it, meaning that we can actually go find the dot product between VU and then add that to the dot product of U and W. So that's very interesting. So remember, again, these are dot products. And then lastly is that if you have a zero vector and you dot it with any vector, then your answer is going to be the number 0. Another cool thing is that if you have vector time dot itself, that's actually going to give you the magnitude of vector v squared. So that's is something very interesting as well. So let's go ahead and do example number 1 using our dot product. Very first thing I'm going to do is to make sure that we rewrite vector v as 2, -3, just so that it's easier to see how we're going to apply the dot product. And we're going to let vector w equal to 5 and 3. So you should be able to do A through F on your own, so you might want to pause the video here. So let's go ahead and do vector v dot w. So remember, we're going to get our x components and multiply them. And we're going to add it to the vertical components being multiplied and find that this answer is actually equal to 1. Now, if you know v dot w, then you know w dot v from the property that we talked about. If you're doing v dot v, so let's do that. So that's going to be 2, -3 dot 2, -3. Again, we're going to get the horizontal, multiply them together, and I'm going to get 4. Plus, then I'm going to multiply -3 times -3, I'm going to get +9, and the answer to that is going to be 13. So we do not take the square root of it. That would be the magnitude. So we're just going to leave it just like that. Now let's multiply vector w times vector w. So we're going to have 5, 3 times 5, 3. So when we do that, we're going to multiply my 5's together. We're going to add the multiplication of my 3's together, and we're going to find that to be 34. Now, because we know that w dot w is equal to our magnitude of w squared, then I take the square root of both sides. I'm going to find that the magnitude of w is the square root of 34. And similarly, we could do that for the magnitude of v by finding that to be the square root of 13. Alright, so the next thing we need to do is go find the angle between two vectors. So let's come back up here and talk about our formula for that. So we talked a little bit about it on the previous page. So what we do know is that the cosine of theta is equal to our dot between our two vectors, and then divide it by the magnitude of each of those vectors. Again, we could use double absolute values or just a single one. And then, so remember, if we're going to go find our angle, the last thing we're going to do is actually do the inverse cosine of that fraction. Now remember, at the top we're going to have a number because the dot product just gives you a number. At the bottom we're going to have magnitudes, and those are just numbers, which is good because that's how we're going to go find our inverse cosine. Okay, so we'll practice that. So let's go find the angle between v and w. So to find the angle between v and w, so I'm going to write down our formula. Cosine of theta is equal to V dot W over the magnitude of V over the magnitude of W. So in our case, V dot W, we already found that to be 1. And at the bottom, we're going to find the magnitude of V, square root of 13, magnitude of W, square root of 34. Now I'm going to show you this, that remember that if they're both radicals, we can actually go find the calculation of 13 times 34 and put it right here. Alright, so in our calculator, the last thing we need to do is make sure we are in degree modes and then take the inverse cosine of our fraction 1 over the square root of 442. I'm going to make sure I check my mode into degrees. And then I'm going to do inverse cosine of 1 divided by the square root of 442. And that gives me an angle of about 87 degrees. So I'm going to come over here and write down about 87 degrees. So let's take a look and see if that kind of makes sense. If we take a look at our graph of these vectors, I would be at 2, -3. That's vector V. W is at 5. 1, 2, 3, 4, 5. 1, 2, 3. So we can see the other vector. So we're claiming this angle right here is our 87 degrees. And it does look like it could be that. Alright, so moving right along, the other thing we can do is determine if vectors are parallel or perpendicular to each other. Another word for perpendicular is orthogonal. So we can see if vectors are orthogonal to each other, that means perpendicular to each other, or whether they're parallel. So let's take a quick look about vectors real quick. So one of the things to realize is that if I have a vector, we'll call this vector U, and I have another vector, doesn't matter where it is. If I have another vector, we'll call it vector V. If they're going in the same direction and I place them graphing on the graphing axes, we're going to see that vector V is going to be right here. And the angle between them is equal to 0. And so cosine of 0 degrees, however, is equal to 1. So we're going to use that fact in just a second. However, if we have vector U, which looks like this, and I have vector V, let's say that looks like this, such that it's perpendicular to each other, what happens is that the cosine of 90 degrees is equal to 0. So we're going to use that fact in just a second. So it says vectors are parallel if the angle between the vectors is 0, or we find that the cosine of 0 is equal to 1 or -1. The reason why the -1 works, well, what if my vector was on this direction? So we would find that to be 180 degrees, and then the cosine of that is actually -1. Alright, and then vectors are orthogonal if the angle between them is 90 degrees, or cosine of 90 degrees is equal to 0. But that also means that when we do our dot product, that also has to equal to 0. So let's see if these guys are either parallel or perpendicular to each other. So let's first find A dot B and see what we get. We're going to multiply 3 times the 6 plus the -1 times the -2, which is a +2, and get that to be 20. And we can go ahead and find the magnitudes of each one of those. So let's do that. Magnitude of A. Remember, we can just, using Pythagorean theorem, we square the first one. We square the second one, and we get the square root of 10. We're going to go find the magnitude of B. Doing the same thing, squaring the 6, I get 36. Squaring the -2, I get 4, and I get the square root of 40. So what this says is that we need to go find cosine of theta. It's going to be our dot product, which is 20, over the square root of 10 times the square root of 40. Remember, we can put those in together like that. So now I'm looking at the square root of 400, which, believe it or not, is 20. So we found that the cosine of theta is equal to 1. That means they are either going in the same direction, so that theta is equal to 0, or they're going in opposite directions such that theta is equal to 180 degrees. In our case, they're going in the same direction because it's a positive 1. So what we find here is that vector A is parallel to vector B. Now let's try the same thing with part B. So we're going to first go find vector C dot vector D. Remember, that is just a number. Getting my x components together, multiplying, getting my y components together, multiplying, adding them together, I get 0. So I can stop right there, because if I have cosine of theta is equal to my dot product over my magnitudes, it doesn't matter what my magnitudes are, this is still equal to 0. So cosine of an angle that's equal to 0, that means theta must equal to 90 degrees, which means that vector C is perpendicular to vector D. If we move on to the next page and the next handout, we also see we're looking at example number 3 that says that we need to decompose a vector into 2 orthogonal vectors, which means we need to find a vector that has a projection of V onto W. And then they tell you where V1 is parallel to W and V2 is perpendicular to W. So let's come back up to the first page where we have our projection of V onto W. Remember, this is the formula that I said that I would give you. So essentially what we want to do is we want to create a vector V into 2 parts. And we're going to call them V1 and V2. And the big thing is that V1 and V2 are perpendicular to each other. But more importantly, we're going to find that V1 is going to be parallel to vector W. So we can find V1 by getting the dot product of V dot W, dividing by the magnitude of W squared, and then giving it the direction of W. So this is our formula that we're going to use. So we've already written it down on the previous page in our notebook as things to know, but this will be given. But we also need to use this formula down here on our second page. So I'm going to rewrite our formula that says if you're looking for V1 and V1 is parallel to W, then V1 is going to be V dot W over the magnitude of W squared dot W. So let's see how that works. So notice we have V and we have W, and our job is to find V1, which is parallel to W. So we have our formula that says first thing you need to find is V dot W. So doing the dot product, I get 3 plus a negative 1, which is equal to 2. I also need to find the magnitude of W. So let's go find the magnitude of W. I square the x component, I square the y component, and I take the square root. So now we're ready. If you want to find V1, you get the dot product, which is 2, and you get the magnitude. In our case, it's the square root of 2, and you're going to square it. Then you're going to multiply it times vector W. So far we have 2 over 2, and our vector W is 1, 1. So we're going to find that V1 is actually 1, 1. The question now is, how do I find V2? Well, remember that V1 plus V2 has to equal to V. So let's get our V and subtract V1, and that will give us our V2. So right here I'm going to write down that we're going to get vector V and subtract vector 1. So vector V is 3, negative 1, and we're going to subtract 1, 1, because that's what we found up here. which means we can find that this is going to equal to 2, and then I subtract, I'm going to get -2. So in terms of a picture, what we have is 1, 1 is, this is W. So for V is 1, 2, 3, -1 is right over here. So what we want to do is create some horizontal guy right here and then some vertical guy right here. This one's going to be V1 and this one's going to be V2. So we can see how V1 is the same thing as W, and we could see how this one will be over 2 and down 2 to get us V2. So it's working. Let's try number 4. A girl is pulling a wagon with the force of 50 pounds. How much work is done in moving the wagon 100 feet if the handle makes a 30-degree angle with the ground? So if we take a look at it, is that we have our wagon, it's on the ground, and it's being pulled this direction at 50 pounds. But remember, the angle that it makes with the ground, that's this guy, is 30 degrees. So let's break up this into a horizontal component and a vertical component. So in order to do that, we're going to find that the force vector is going to be 50 cosine 30 degrees, comma 50 sine 30 degrees. But we know those values, so that's going to be 50 square root of 3 over 2 and 50 times 1/2. And that's going to give us 25 square root of 3, comma 25. So there's vector F, so we know that one. And then you want to see the distance that you want to go. Well, the distance we want to move is 100 feet this way, by 100 feet. So the vector component for distance, the vector component for that is going to be positive 100 towards the right, the direction in which she's pulling, and 0 up and down. That's what we want. So if you want to find work, you're going to get the vector F and you're going to dot it with the distance vector. So we're going to do 25 square root of 3, comma 25, dot 100, comma 0. And remember, the dot product is just going to give us a number. That's how much work we're going to be doing. So that's going to give me 2500 square root of 3 plus 0, because 25 times 0 is 0. So this is how much work is being done for this. So I'm going to go back to the very first page. I think we have some extra room there, and do another example about projection. So let's say we have vector V and we want to project it onto W. So what that means is that we're going to make components of vector V such that one of them is parallel to the W and the other one is perpendicular to the W. So the one that's parallel, that's this one down here, we're going to call that one V1, and the one that's perpendicular, we're going to call that V2. So let's see if we can find what those components are. So remember, for V1, we need to go find V dot W, get the magnitude of W and square it, and then multiply it times W. So V dot W, so that's where I'm doing my dot product. I'm going to get negative 15 plus, add those, I get negative 14, which is equal to negative 29. Our magnitude of W is going to be the square root of 25 plus 4. So remember, I'm squaring the 5 and squaring the negative 2. And then when we're done, we're going to square that. So when I do that, I'm going to get 29. and I need to multiply that times W. W is 5, negative 2. So now I'm going to find that I'm going to get a negative 1 times 5, negative 2. So V1 is going to be negative 5, positive 2. So notice this one is not quite the same as W, but pretty close. But we do have the same slope, so that's good. So we do know it's going to be parallel to W. Alright, so now we got to go find V2. So we found V1. V1 right here, we could see it on our graph. We go negative 5 and up 2. We can see that that is indeed V1. So now let's go find V2. To find V2, remember that you get your original V and you subtract your V1. That's from this part right here. So I'm solving for V2, so I'm subtracting V1 to both sides. So V is negative 3, 7, and we're going to subtract negative 5, 2. Remember, I like to distribute my negatives and then just add. So negative 3 plus 5 is 2, and 7 plus a negative 2 is 5. So if we take a look at this vector, we could see that it is over 2 and up 5. And that concludes this video.